Enjoying physics. So continuing our journey on understanding the physical quantities involved in our topic of motion in one dimension. Today we are going to discuss velocity and speed. So what is velocity? Velocity is change in position of an object with respect to time, or we can say change in position divided by time. And finally we can say that it is displacement divided by time. So here velocity is xf minus xi divided by tf minus ti, where xf is the final position, xi is the initial position, tf is the final time, and ti is the initial time. We also represented it by delta x by delta t, where delta represents difference. Again, velocity is a vector quantity. It has both magnitude and direction, and the standard unit is meter per second. So continue our example from displacement and distance, where we had made the table and analyzed all the movement of the object. So we knew that the displacement for our first data point was 3 meter, second was 5 meter, and then it was for the fourth data point was 1 meter, 0 and -1. So here we can find out what is the velocity in these cases. So if we see that the displacement is 3, time taken is 3. So this will be 3 divided by 3, that is 1 meter per second. For the second data point, we have displacement of 5 meter and the time taken is 5 seconds. Again, the velocity will be 1 meter per second. For the fourth data point, we have a displacement of 1 and the time taken is 9. So this will be 1 divided by 9. It's approximately 0.1 meter per second. For the fifth data point, where our displacement is 0, so our velocity will be 0. That will be 0 by 10. And for the last data point, that is the sixth one, we have a displacement of -1. So -1 and the time taken is 11 seconds. So it's approximately 0.091 meter per second in the, that is with the minus sign showing it to be going towards the left in the negative direction of the x-axis. So coming to distance, distance is the total path traveled per unit time. We can say total path length traveled divided by the time taken, and finally we can say that it is distance divided by time. So looking at the table again, we can find the speed, and speed is a scalar quantity which is defined by its magnitude only, and SI unit is again meter per second. So we can find the speed. Here the distance traveled was 3 meter, time taken was 3 seconds. So the speed is 1 meter per second. For the third data point, we have the distance traveled to be 5 meter in 5 seconds. So again the speed is 1 meter per second. For the fourth data point, the distance traveled is 9 meters, time taken is 9 seconds. So again 1 meter per second, and correspondingly we can find that it is 1 meter per second for all the data points. Okay. So if you analyze this problem, you will find there is one loophole in this. At this point, at the data point number 4, you can see that the velocity which is there, that is 0.1 meter per second, and the sign says that this velocity is in a positive direction of the x-axis. But as we have already analyzed this motion, we found that the object has came here after retracing its path. So when it is here, the direction of velocity is towards the left, but here it is showing towards the right. So why this is happening? So you can say the answer lies in the difference between average velocity and instantaneous velocity. Whatever calculations that we have done in this table, they corresponds to average velocity. So this is average velocity and this is average speed. So we need to look into instantaneous velocity. What is instantaneous velocity? Velocity at a particular instant of time. So for that we need to understand what a function is. Okay. Basically, function is a relation between inputs that corresponds to a particular output. A general definition of a function says y is equal to fx, where x is the input and y is the output. So it's a relation between inputs where each input corresponds to a particular output. You might have learned coordinate geometry, and in that you have learned about straight lines. So we'll take an example here. This is the y-axis, this is the x-axis. This function could be anything. We'll take an example with an equation of a simple straight line, that is y is equal to x plus 3. Okay, so this is also a function where each value of x will have a corresponding value of y. First of all, we plot this function or the straight line. So we can say that this is the origin, and at x equal to 0, the value of y will be 3. So this will be 0 comma 3, because x is 0 and y is 3. And similarly, if y is equal to 0 at you can say this x-axis, for y is equal to 0, x will be minus 3. Minus 3 comma 0. So if you, and as we know that these are the first order equations and this is the equation of a straight line. So we have the 2 points and it is enough to trace the curve. So this is our straight line which satisfies this function. And if you take any value of x, suppose you have a value of x to be 1, that is, this is 1. So the corresponding value of y will be y is equal to 1 plus 3, that is 4. So the coordinate of this point will be 1 comma 4. Now applying a knowledge of functions to instantaneous velocity, we define a function x is equal to ft, where x is the position of an object and t is the time. Here t is the input and x is the output, which satisfies this function definition. Currently, we assume any arbitrary function. For that, we trace a curve. So this horizontal axis will be t, here it will be time, and the vertical axis will be the position. And we make an arbitrary curve. We consider a point P which has coordinates t comma x, which satisfies this function. Our target is to find the instantaneous velocity at this point P. So currently we have a knowledge of average velocity, that is change in position divided by the time interval. So to calculate the average velocity, we should also consider another point. So we consider another point Q, which is at a distance of delta t along the horizontal axis. This is t and this will be t plus delta t. So according to our function definition, f t plus delta t, this will give the output to be x plus delta x. So here the coordinates will be t plus delta t, comma x plus delta x. If we join these 2 points P and Q, it will touch the t axis and makes an angle theta. Okay. And now with our definition of average velocity, v is equal to delta, or we can say the change in position. So what is the change in position? Here we have the at q we have the position of x plus delta x minus the initial position is x. The time at point q is t plus delta t, and the time at p, that is the initial time, it is t. We can also write this as f t plus delta t minus ft. This is according to our function. Upon this t will cancel out, this will be delta t. Even if you make this right angle triangle, so this will be point Q, this will be point P. We assume it to be a point A. This is the angle theta. So this is, you can say this is delta x, this is the change in position, and this is the change in time. This will be delta t. So we can also write this as delta x by delta t, and that will be equal to tan of theta, because this will be perpendicular, this will be base. Okay. Now our target is to find the instantaneous velocity at point P. So what we do, we reduce this delta t to a very small value. So we can say that it is tending towards 0. As this delta t tend towards 0, this point Q will move along this curve towards point P, and in that duration both delta t and delta x will tend towards 0. So delta t will tend towards 0 and delta x will also tend towards 0. But here we see that this is the ratio of delta x by delta t. This ratio is not necessarily going towards 0. It could be any value. So we say that here we make a differentiation between instantaneous velocity and the average velocity. So in case of average velocity, we use a bar over any physical quantity where we say average. So here v bar is an average velocity. So we define instantaneous velocity to be v, that will be limit of average velocity where delta t tend towards 0, or we can say limit of delta x by delta t where delta t tend towards 0, and we say that this is dx by dt. That is derivative of x with respect to t. If you visualize this in the figure, the curve, you can say that as delta x and delta t approach towards 0, that is the point q starts to move towards point P, the slope of this line, the line PQ, this will gradually become tangent to this curve. So finally, this will be a tangent. That could be any angle. You can say that this is alpha. So when this happens, so we say that the instantaneous velocity at point P is a tangent to this curve at point P and at time t. So we can say that this is the slope of the tangent. The instantaneous velocity is the slope of the tangent to a curve at point P and time t. So this is how we define the instantaneous velocity. Now, even if you look at the previous example where we have considered the average velocities and average speed, where we considered motion only along the x-axis, where we had the markings of 1, 2, 3, 4, 5, -1. So using the concept of average velocity, we can even get the sense of the direction of the motion, in which direction the object is moving. So if we consider the data point 3 and 4 here, so if you consider the motion only in this duration, that is between the time of 5 and 9 seconds, so you can get a sense of the direction of the motion. So suppose we have already defined that average velocity is xf minus xi divided by tf minus ti. Here xf is the final position, xi is the initial position, tf is the final time, ti is the initial time. So now we consider the motion between data point 4 and 3, where the time was 9 and 5 seconds. So we can see that what was the position at data point 3 and 4. So this will be our final point, that is 4. Here the position is 1, xf is equal to 1. Initial position was 5, xi. The time at data point 4, that is 9, and the time initial is 5, that is at data point 3. This will be minus 4 by 4, that will be minus 1 meter per second. So here this negative sign is showing that the motion of the object is towards the left. So even with the concept of average velocity, if we change the duration of the motion, or you can say uh, we change the duration of the study of the motion, so even then also we can get the sense of direction. Okay. So but again this will be average velocity only. If you want to find the instantaneous velocity, that is derivative of x with respect to t, we need to have a function definition. Now as we have learnt about the derivative, moving further we are going to learn about the inverse of derivative, that is integration. Integration has a versatile application in physics, and mainly it is used to find the area under the curve, and in a way to find any physical quantity that is involved in a particular concept. So again, to learn the concept of integration, we are going to use our prior knowledge of average velocity. We have defined average velocity, that is v bar is equal to delta x by delta t. We take this t towards the left hand side and we say that delta x is equal to v bar into delta t. Okay. Now there are two scenarios. In one case where the velocity is constant, the average velocity is constant. So along this horizontal axis we have t. On the vertical axis now we have here average velocity, or we can simply say velocity. Case 1, velocity is constant. If velocity is constant, this line will be, you can say, parallel to the t-axis. And if you want to find the area under this curve between points A and B, that is this area, we simply can see that this is like a rectangle. So x will be total displacement, and this will be equal to v bar tb, that is the final time minus the initial time. So this will be our, you can say, length, and this will be our breadth. So we can find the total displacement, that is area under the curve. In the second scenario, case 2, velocity is not constant and it is some function of t. It could be any arbitrary function. So we can say that This is that arbitrary function, and if you want to find the area under the curve between points A and B, this area we need to find. So looking at this curve, you have a feeling that we cannot just simply multiply the V and TA minus TB, just like we did in case of the constant velocity where it was a rectangle. So, but here you can say the velocity is not constant. So we need to devise some other method to find the exact area under the curve. So what we do, we take a small strip where the time is ti minus 1 and this will be ti, and we find the area of this strip. As this strip is, you can say, very small, or you can say its length is very small, so we can assume that for such a small length the variation of velocity is negligible. So we can again here consider this small strip to be a rectangle, and we can write that delta x is equal to v into ti minus ti minus 1. As we have said that velocity is not constant, it is some function of t. So we define a function v is equal to ft. So here we can write the area of this strip will be ft or fti, because we need it at this point, ti minus 1. Okay. Now to get the total area under this curve, we need to consider more such strips, and we say that the total number of strips that will cover this whole area will be n. So we say that total displacement will be summation of I is equal to 1 to n f ti ti minus 1. Now if we reduce this length, or that is ti minus 1, to a very small value, such that the number of strips tend towards infinity, you can see that as we reduce this the length or the width of this strip, if we keep on decreasing this ti minus 1, the number of strips will keep on increasing, and we reduce this difference to a very small value that we say that n tend towards infinity. So we can say that I is equal to 1 to n is equal to infinity f ti minus 1, and this can be written as integral of ft into dt. This is ft dt, and we can do it between the limits, that is, so we can say that the total displacement, that is area under the curve, is integral of ft over dt between the limits a to b. So this is the definite integral, and it has some definite value. So this is how we do integration and find the physical quantity involved. Okay.